So delta G0 determines the spontaneity of a reaction, whether it's going to occur or not. K, the equilibrium constant, determines how far the reaction goes towards the products. If we have a large K and a more negative delta G0, the products will be favored. If we have a smaller K and a more positive delta G0, the reactants will be favored. Derive the relationship between K and delta G0. So we're going to start with this. Delta G is equal to delta G0 plus RT, natural log of Q This is the result. So here we're looking at an equilibrium between A and B. If K is less than 1, then the reverse reaction will be spontaneous under standard conditions, right? Because under standard conditions, these are going to equal 1. And if Q is less than 1, K is less than 1, then this reaction is going to proceed until Q becomes equal to K. So this has to get smaller, we get the reverse reaction. If K is larger than 1, from standard conditions where Q equals 1, the forward reaction will be positive. At equilibrium, with standard conditions, Q is equal to 1, and the reaction's not going to go in either direction. So calculate delta G0 at 298 K for this reaction, and we're given the equilibrium constant. Oops. Nope, not that either. So we're using that equation, delta G0 for the reaction is equal to negative RT natural log of K. So we're going to have negative, and the ideal gas constant, 8.314 joules per mole Kelvin, and the temperature given, 298 Kelvin. Natural log of K, and K here is 81.9. So if we express that in kilojoules minus 10.9 kilojoules would be the standard Gibbs free energy change. Any questions? So the free energy change depends on the equilibrium constant. The free energy change also depends on the temperature. We can combine those two and get this equation in a straight line form. The natural log of the equilibrium constant is equal to negative delta H over R times 1 over T plus delta S over R. And so if we plot natural log of the equilibrium constant versus 1 over the temperature, we'll get a straight line. The slope is equal to negative delta H over R. The intercept is equal to delta S over R. This is useful over a limited temperature range. You can't go with a really wide temperature range. But this is one way that you can find out what delta H0 and delta S0 are, is you can measure K as a function of temperature. We can also express that in a two-point form, and this should look a little bit familiar. Natural log of K2 over K1, etc. And so here we can find delta H0 by measuring K at 2 different temperatures, or we can find K if we know delta H0 and the equilibrium constant at 1 temperature. Thankfully,